Uh, and dear students, the topic of today's lecture is chirality and plane of symmetry. Uh, we have been discussing about chirality, asymmetric centers, or chirality centers, or stereo centers, or stereogenic centers. In this lecture, we will see what is the relationship between the plane of symmetry of a molecule and the chirality. Plane of symmetry is the criteria which a molecule should fulfill for it to show the phenomena of chirality. So let us start this lecture. In the last few lectures, we have been discussing about these terms: chirality, asymmetric centers, stereo centers. And the big question is, how do we recognize if a molecule is chiral? What are the different methods available which can tell us whether some molecule is chiral or not? For that purpose, there are some methods available. Actually, there are three methods available by which you can easily tell whether a molecule is chiral or whether the molecule is not chiral. So these methods I'm going to explain in detail in this topic. So we'll start with the first method, which is very much known to you. The first method obviously is a very simple method. What you have to do, you have to build a three-dimensional model of a molecule, and for this purpose you need some physical models. You need some models of these molecules, three-dimensional models. And after you build the three-dimensional model of a molecule, then what you have to do, you have to build the model of its mirror image. And if the two models are superimposable, if these models are superimposable on each other in any conformation, a molecule can have so many conformations. You have to remember that if the two models are superimposable in any conformation, then the molecule will be achiral. So, superimposability and non-superimposability, I have discussed this topic in great detail in the previous lectures. So if the two models are superimposable in any conformation, then the molecule will be achiral. And if they are non-superimposable, then the molecule will be chiral. Right? So I will give you some examples by which this can be clear. This building of three-dimensional, models of a molecule. This is the model which I have already given to you. Let's repeat it. And this is a 3D model of a molecule, three-dimensional model of a molecule, where this is the central atom, central carbon mostly, and different colored groups represent different groups. Different colors means different groups. So this central atom is attached to 4 different groups. This is the model of the original molecule, and this is the 3D model of its mirror image. Its mirror image. So what you have to do, you have to superimpose them. If they are superimposable, then the molecule will be achiral. If they are not superimposable, then the molecule will be chiral. Right? If they are superimposable, the molecule will be achiral. If they are non-superimposable, the molecule will be chiral. Here, these two molecules that I have given here, they are non-superimposable mirror image. Then we can easily conclude here that this molecule will be chiral because it produces two non-superimposable mirror images. So this molecule will be chiral. So first method is building a 3D model of a molecule, then checking whether those two models, which will be mirror images of each other, they are superimposable or non-superimposable. Let's move ahead. Second method is very much simple, which I have already discussed to you. Second method, what you have to do, you have to look for a stereogenic center or asymmetric carbon. In other words, what you have to do, you have to look for an atom, carbon atom, which is attached to four different groups, such carbons are known as stereocenters, or they are known as chirality centers. So if there is a stereogenic center or asymmetric center present in any molecule, then it will be chiral. Any molecule, I have written here, any molecule with one chirality center, means any molecule which has a carbon which is attached to four different groups, as it is only stereocenter, means any molecule which only has one asymmetric carbon or one stereocenter, this molecule will always be chiral. It will always be chiral, right? So but there are some molecules which have two or more than two asymmetric centers or chirality centers. Those molecules may or may not be chiral. So any molecule with multiple chirality centers, I repeat what I said in the previous slide. I said that if a molecule has one chiral center, one asymmetric center, it will always be chiral. Means any molecule which has one asymmetric center or one carbon which is attached to four different groups, it will always be chiral, with no exception. But there is a problem with molecules which have multiple chirality centers or multiple asymmetric centers. Those molecules with multiple asymmetric centers, they may or may not be, I have written here, they may or they may not be chiral. Example is given here. You see this molecule here, it has two chiral centers here. There are two asymmetric centers, right? Means this carbon here, it is attached to four different groups. This is group 1, group 2, group 3, and this one is group 4, right? So this carbon is attached to four different groups, and this carbon is also attached to four different groups, right? But despite having two, so this molecule has two chirality centers are there. This molecule has two chirality centers, but yet the overall molecule is achiral. I must mention here that chirality and achirality is a property of a whole molecule. It's not the property of a single center. Chirality is a property of a whole molecule. So on a whole, this molecule here, despite having two chirality centers, the molecule is achiral. Same is the case with it. This is its mirror image. Same is the case with its mirror image. So this is achiral, and hence it will be optically inactive. I will explain this term in our upcoming lectures, what is optical activity and inactivity. But for the time being, I'm going to, this is a meso compound here. It's called as meso compound. And this molecule, despite having two chirality centers, it is achiral. Reason being, it has a plane of symmetry, which I am going to explain in detail in coming slides in this lecture, in this very much lecture. This molecule has a plane of symmetry. That's why this molecule is achiral. So you should note here, you have to note a very important point here, that the presence of a chirality center is not the sole criterion for a molecule to be chiral. So there has to be some other criteria through which we can say that whether a molecule on a whole is chiral or it is achiral. You can see here, this molecule has two chirality centers, yet the overall molecule is achiral and optically inactive. So what is the best criteria then? So looking for, we can conclude here, so looking for stereo centers or asymmetric centers in a molecule can be misleading. It can mislead you, as in the case of last molecule that I showed in the last slide. It can be misleading because there were two chirality centers, yet the overall molecule is optically inactive, yet the molecule is achiral. So there has to be some other criteria. If you take the example of this molecule also, cyclohexanol, this molecule has it has no chirality center. I have numbered this molecule. This is carbon 1 here, this is carbon 2, carbon 3 and carbon 4. You see carbon 1, it's attached to one OH and one H group, and two ring substituents are there. Where are they? They are ring substituents are here. This is one ring substituent attached to it, this is another ring substituent attached to it. But you see these two ring substituents they are identical, they are not different, they are identical. You have a CH2 here, you have a CH2 here, then you have a CH2 here. From this side you have a CH2 here, then again you have a CH2 here. From this side if you go, you have a CH2 here. From this side also you have a CH2 here. So both these substituents are identical. It means that the carbon 1 is not attached to four different groups. So this molecule has no stereo center, hence this molecule will be achiral. It will not be chiral. There are some more examples. This is cyclohexanol, this molecule. In previous slide we saw cyclohexanol. This is cyclohexanol. Cyclohexanol. Here you see this carbon number 1 here. This is the carbon number 1 here. It's attached to you see it is attached to one OH group, it is attached to one H hydrogen, and two ring substituents are there. But here you see these two ring substituents are non-identical, they are not identical. Why? Because from this side you see you have a CH2 here, then you have a CH2 here, but from this side you have a CH here and a CH here. So these two substituents are different, hence this C1 carbon here, this C1 carbon it's a stereo center, hence we say it's a chirality center. It's a chirality center because it is attached to four different groups, hence this molecule will be, we say this molecule will be chiral, right? Moving on to this molecule, this one. You see this carbon number 1 here, 1 2 3 4. This carbon number 1, if you see it is attached to one chlorine, it's attached to here this ring substituent and this ring substituent, and obviously there is a hydrogen here, right? But these two ring substituents, from one side you have a CH2 here, from other side you have a CH2 here, from this side you have a CH3 here, and from this side you have a CH3 here, then from both sides you have a CH2 here. So these both sides are similar, hence this carbon here, this carbon, it's not attached to four different groups, hence this molecule will be achiral. Moving on to this molecule, you have this carbon here, this carbon number 1, it's attached to chlorine, right? It's attached to hydrogen also, it's attached from one side to CH2, From this side you have a CH2, from this side you have a CH2, but from this side you have CH3, CH3. These are two methyl groups here. So these two ring sides are different. So it means that this carbon here, C1 carbon, is a stereo center. It is a stereo center. Hence this molecule will be chiral. Similarly, you have a hydrogen here, right? So this carbon here, it's attached to 4 different groups, as you can easily see. So this molecule is chiral. Here, at this carbon you have a methyl group. You have this ring substituent here, you have a ring substituent here, and you have a hydrogen. But these two ring substituents from both sides, they are identical, hence this molecule will be a chiral. So I hope it's very clear to you now. You can easily identify which molecules are chiral and which molecules are not chiral. So far we have discussed 2 criteria. Let's move to the third criteria, which is very important. This criteria is the criteria of plane of symmetry, or it's also called as a mirror plane, right? This is the final way. A final way to determine whether a molecule is chiral is to examine its symmetry. Is to examine its symmetry. Is to examine its symmetry, right? A molecule can have different symmetry elements present, like center of symmetry, like alternating axes of symmetry, or plane of symmetry. These different symmetry elements can be present in a molecule, but the only kind which is our concern here is the plane of symmetry, or a mirror plane. So we will limit our